to determine how much dissolved oxygen is in the water. Dissolved oxygen, or DO, is related to temperature, since cold water holds more oxygen needed for aquatic life to survive. Low or fluctuating DO levels can harm the aquatic life. Using the smaller vial, fill it with water all the way to the top, so there is no air left in it. Drop 2 dissolved oxygen tablets from the blister pack marked DO into the test kit and screw on the cap. If your vial is filled properly, some water will overflow as you do this. Now gently turn the vial end to end for several minutes to dissolve the tablets. Do not shake it. Once the tablets have dissolved, wait 5 minutes for the color to develop. Now compare the color of the water with the dissolved oxygen chart on the card. Select the color that most closely matches your water sample and note the value, 0, 4, or 8 ppm, or parts per million. The higher the number, the more dissolved oxygen is in the water. Since the water temperature affects the ability of oxygen to dissolve, you will also determine the DO saturation percentage, using your results from these 2 tests and the chart in the test kit manual.
Well, looks like they've got it sussed there, haven't they? Yeah, looks like they've got it sussed. Looks like there is dissolved oxygen in water, pond water, after all.
Absolutely, yeah.
Looks like we're wrong.
Yeah, I know, yeah.
Looks like we've been proved wrong.
Yeah.
You know, all these school kids going to school, been conditioned into thinking that dissolved oxygen is in pond water.
Oh, well, yeah, but when you think about it, really, the dissolved oxygen, well, let's say the oxygen actually is contained within those tablets.
Yeah, even I think that dissolved oxygen is actually contained in those tablets. Yeah, sure. That's why they're called dissolved oxygen tablets.
Yeah.
You can be very intelligent and very good at what you do, and you can still be stupid.
Yes. Yeah, well, we're back again. Annoying people with our views and opinions because a lot of people dislike to hear other people's views and opinions. Yep, a lot of people do dislike hearing other people's views and opinions, especially this guy here who what's his name? Mr. Don
London.
Who?
Was it London?
No, not London. Lincoln. Dr. Don Lincoln, of all people. Yeah, he wouldn't like our views and opinions. I reckon he'd get enraged if we said to him that he's full of shit.
Trying to turn green.
Well, I don't think he'd turn green. He doesn't look like the Hulk at all. And there's no such thing as the Hulk anyway. People don't turn green, metamorphosise into this monster. Lou Ferrigno. I mean, how can Bill Bixby turn into Lou Ferrigno?
Oh, yeah, I know. You tell me.
Come on.
Comment below. Love to know.
If anyone out there knows how Bill Bixby can turn into Lou Ferrigno...
And Lou Ferrigno can turn into Bill Bixby.
And Lou Ferrigno can turn back into Bill Bixby, let us know. Drop us a comment below. And then, you know, we'll have to do a bit of research on what you say. But as far as we're concerned, you know... This guy certainly won't turn into the Hulk if we tell him that he's full of shit.
Absolutely, yeah.
But, yeah, of course, yeah. So how are you, Peter? Are you well? Are you well? Or are you well?
I'm very well, thank you. And we both hope you are all well too. Yes, all of you.
Yes, we've had a lovely day today. It's been very nice and peaceful. Very spiritual as well.
Oh, yes, and we had quite a nice dinner as well.
Absolutely, of course. Since it's September and the weather's been absolutely gorgeous, I suppose.
Absolutely, yes.
It's been very reminiscent. Been very close, hasn't it? Very close. That's the idea of the game. But so what have we got on for everyone's displeasure for tonight then, Peter?
Well, for everyone's displeasure. Oh, mind you, saying that we did actually go shopping in Tesco's, and I have started to see the stock being depleted from the shelves.
Oh right, yeah. Oh, it's pretty much like the shelves behind us.
Yeah, basically, yeah.
They're becoming more emptier.
Yeah, apparently it's supposed to go on for a couple of years, apparently.
a couple of years. Well,
It hasn't gotten worse either.
I reckon it will go on for quite some time. Yeah,
Yeah.
it will go on for quite some time. This Brexit, well, it's ongoing, isn't it?
Absolutely, yeah.
I mean, Brexit, and see, one thing I dislike about the government, and that is they don't plan for things. So they do something because that's what they want to do, and any consequences they'll sort out
Afterwards.
afterwards.
We'll deal with that.
We'll deal with that afterwards. You know, and the people just have to put up with it
Yeah, I know, yeah.
because that's how the UK government actually operates.
Anyway,
But I don't vote, so
neither do I. Anyway,
I'm sensible.
come on.
I've got nothing to vote for. That's why.
Oh, right. Let's see if because if you
Now, if I was living in Scotland, I'd have something to vote for.
Yeah.
Independence. Absolutely, of course. But I'm living in England, and there's nothing to vote for.
Yeah, unless you want to be a football hooligan or something.
Unless
like
you
that.
want more of the same.
Oh, right, more of the same. More coffee shops.
More coffee shops, more cost of coffee,
More restaurants.
more bullshit.
Absolutely, yeah.
Absolutely, of course. So, what have we got
Oh,
on for
right,
everyone's
yeah.
displeasure?
So, for everyone's displeasure, what we're going to talk about? We're going to talk about Dr. John D. And we're going to just highlight a video of his because we've actually come across somebody who has the same views and opinions as we do.
Absolutely,
Isn't that great?
sure. Isn't that lovely?
Got some. We did mention on one video about that the moon traverses the sky along with the stars, not the wandering stars, but the majority of the stars, all moves at the same rate. And John, blood's thicker than water, he gave us a video of time lapse showing it, and we've also got another video
From Alexander that we're going to show everyone.
Yeah. Because to me, that is the dead giveaway that the moon is not a single entity orbiting the Earth.
Yeah, that's moving
Can't be.
independently of the stars.
Yeah, can't be.
Yeah,
Impossible.
yeah, sure.
So we'll have a look at that. We're going to have a look at blue marble. Apparently, blue marble.
Yeah.
Is it blue marble
yeah,
science?
Blue marble science. Yeah,
Apparently, he detected an earthquake with his torsion balance.
absolutely. Yeah, all thanks to Cavendish. So really, what Cavendish did was actually designed a seismometer.
Yeah, basically. However, see, this is the thing these globies don't realise, and that is the science can debunk other bits of science.
Yeah, absolutely,
Yeah.
of course.
So the torsion balance can actually debunk something else within the science community. Just like here with this guy,
Absolutely.
can't prove light is electromagnetic, and we're going to highlight one particular experiment that debunks the very idea. Oh no, sorry, we're going to put forward one of this guy's theories
It's only a theory.
on how light is electromagnetic that debunks the idea that light is electromagnetic.
Yeah, sure. I think I understood that. Yeah, sure. Of course.
Yeah.
Absolutely.
So and then we've got a few demos on CO2.
A few demos on CO2
and infrared.
Absorption, because we're trying to find.
No, we're trying to.
We're trying to determine what will actually, what kind of light. I'll use it in dittos, like infrared, or what kind of infrared will be absorbed by CO2. We're trying to find what will absorb, what CO2 will absorb.
So we've got a demo to show people.
Absolutely, of course. So what should we do first then? Should we do Dr. John D?
Dr. John D.
Now, we had a few people, after our previous video, we discussed Thomas Young's light wave experiment and stuff, and his whole understanding or ideas on light being wave and not particle. So he came up with the whole understanding of interference patterns, and then there you get your waves.
Yeah, because the only thing that you can use to demonstrate that light is a wave is water, because everybody knows that there's waves on water.
Yeah, and we carried out Thomas Young's experiment that he actually did on water, essentially, to see if we got the interference pattern on water, and we didn't.
Yeah.
So how he arrived Well, how he managed to get an interference pattern with light means that you can't use water in order to demonstrate how light works. You've got to be mad to do
And
that.
that light is a wave.
And also that light is wave. But regardless. But after that video, we had a few people leave us comments, say, "Oh, you want to watch Dr. John D and all this kind of stuff." So here's what we got on the video: the Illumination series Part A Wave, and we watched some of it. I'm not going to say we're going to watch all of it, but you can see here, for example, he talks about Young's interference pattern, where Thomas Young's ideas on light were, well, according to Dr. John D, were mistakenly biased and influenced by his understanding of waterways. But what we would say is that it was Thomas Young's only way of convincing people that light is a wave, by using something that acts as waves. And at the time, the only thing they knew that acts as waves is water, because people could see the waves on the water.
Yeah, well, I couldn't see him sort of getting all the audience in the Royal Institution in the lecture hall doing a Mexican wave.
Oh yeah, well they could have done, couldn't they? They could have all gone this, like that, or they could have just done this, couldn't they?
Oh right, yeah.
Well, absolutely, of course. To Thomas Young, "Hi Tommy, oh but Tommy's here with his wave machine." But so we ended up. We can't leave a comment because he doesn't allow them for his own sanity, really.
But we had an exchange of communication with him,
which we just like to share with people. Here we go, and he writes. Oh, wait there. He writes. So far writes. Wait there. There he is.
He writes everything. "Evening, gentlemen. Thank you for replying. Appreciate it. I have to agree with you. Virtually everything is made up nonsense.
Yeah, absolutely.
Unproven explanation from observation.
Yeah.
The more I research into chemistry, physics and biochemistry, the more I stumble across unproven assumptions, false equivalents and logical fallacies. It is horrendous. The only things you can trust at present is what you can witness for yourself. It all needs a rewrite."
Absolutely, of course, yeah. It's all bollocks, really, at the end of the day, when you really do think about it. And it reminds me of somebody once said to me that everything outside your front door is rubbish. It's bullshit. And, as soon as I walk out my front door and I go into society and I look around me at what man's created for himself, it's bollocks. It literally is bullshit.
Yeah, because there's a lot of people. The thing is that there's a lot of people who put a lot of trust and faith and hope in the cars, in the transportation system, in
their phones,
in their phones,
always
in
on
the
their
technology.
phones,
and the thing
in
is,
their supermarkets,
yeah, but the
in
thing,
the shops,
but the question everyone
consumerism.
Consumerism. But the question people really need to be asking themselves is it making people any happier?
Well, what's it doing for people?
What's it doing for people?
What does it do for people? I mean, could we not improve it?
Because the thing is that some people say, well, look, life is a lot better now than it was 300 years ago. But granted, people have more things to do in their lives. But the thing is the quality of their lives any better?
Any better? You've still got churches. Churches are still prevalent. And people are still religious, and that hasn't changed.
You still have disabled people. You still have
absolutely, yeah,
people who murderers, criminals. You still have thieves. You still have child abusers. You
cheaters,
still have
liars,
cheaters,
blackmailers,
relationship breakdowns. You still have lots of things in society that's plagued man's behaviour for
man's existence.
Yeah,
and so what's changed?
What's changed?
But I would say that money does cover it all up.
Yeah, that's all it does.
Money.
It's like a plaster.
Money's like a plaster, absolutely. Of course. Maybe they should put banknotes around people's wounds.
Oh, well, that's an idea.
That's a good idea, actually. That's what the Bank of England should do. Every time you get a hurt individual, they should go to the bank to get a note to wrap round their wound.
Yeah, that's more or less what happens when, say, if you lost your job, for example. Or
if you lost your job, or if you had an accident at work.
Absolutely, yes.
They'd really bandage it up with a note because they'll pay you compensation.
Yeah.
When you think about it, but what it produces is a society that really couldn't give a shit about other people. because they think, well, you can claim some money. Just claim money. Look, I don't care if you can't walk anymore. Well, I'm not bothered. Just claim off my insurance.
Yeah. There's a subway near where we are. There's a subway, and I walked under there, and they had recently repainted it all because loads of people had put graffiti over it, and so it was all nice and clean. And someone had wrote on the wall, "Who cares? Does anybody care?"
Nobody cares. Absolutely. You're living in a society where people are just paid to care.
Anyway,
unfortunately, I mean, that's the way it is.
Anyway,
that's the way it is. But Dr. John Dee and us do share the same views and opinions regarding science.
Yep.
In that, basically, a lot of it, especially with regard to the natural environment, can't be proved to be true.
It's a bit like Boris Johnson. The thing is that nobody really cares about him.
Nobody gives a fuck
Tory
about
party, the monarchy, his cabinet. Nobody cares about him, really.
Yeah, no, yeah. I mean, it's just ridiculous. I don't know. It's amazing how it all keeps going, isn't it? It's British society, or many societies, to be fair. How do they all keep going? It's ridiculous.
No, come on. There you go. So it's nice to come across someone who shares the same views and opinions as we.
Absolutely, very nice indeed.
Alexander.
Absolutely, of course. So we can get rid of that. Alexander with his moon video. Here we go. Now we did ask. We did.
Now this is, to me, this is conclusive evidence. This is just conclusive that the moon is not a separate entity orbiting the globe Earth.
How long would you think this video would have taken in real time? Because it's a time lapse, but how long do you think it would be?
4 hours?
4 hours. 4 hours seems about right, doesn't it?
Possibly.
4 hours long. So in 4 hours, we can visibly see the moon and two stars moving together.
Oh, right, yeah. Now, the stars
We've got one star there.
Yeah.
One star there.
Bright one there.
And the moon there.
Now, the moon is meant to be about 230,000 miles from
230,000 miles, allegedly.
From the Earth.
No, that's a story.
That's the story.
No,
and these stars are meant to be light years away from Earth.
Yeah, maybe now what people should do is they should find out what stars these are, in the video, okay, and then they should ratio the distances down and make up a little model, and then see.
But the moon is closer, so it would move
faster.
It wouldn't move at the same rate as these stars.
Absolutely, of course, because something nearer to you will move faster than something further away from you.
Yeah.
But when we look at the video, there you go. We can see they move all together in synchrony.
Yeah.
There we go. Lovely, isn't it? Let's play the game.
Okay.
I mean,
this is to me conclusive.
Well, this is what happens in the real world. This is what happens in the real world. You've got the moon and the stars moving together. Okay, so if you've got a universe with the moon close, for example, and stars trillions of light years away, some close to us still, and yet some even further away, billions, trillions of light years away. The stars wouldn't appear to move
at the same rate.
Wouldn't move all at the same
rate as the moon.
They wouldn't move at the same rate as the moon.
Yeah.
Okay, they'd move at different rates across the sky.
Oh, yeah.
But we don't see that. This is clear.
Yeah.
This is real. This is what happens in the real world.
Yeah.
Not in my imagination or on TV or somewhere. This is the real world. Okay. So it's people who think that we're living in this universe with stars trillions and billions of light years away, some close, some far away, even further, some big, some small. The moon 230,000 miles away.
Got mental health problems.
They got mental health problems. This is reality. What you're seeing now
is the real world.
Is the real world.
Oh, yeah.
Okay, this is the real world. So thank you ever so much, Alexander, for that. That was a good one.
Yeah,
if anyone else has got any more, please let us know. Time lapse of the moon and stars working together, or just the stars working together.
No, you want the moon as well, because
Well, you
the
don't
moon
need-
is,
you
yeah, you
don't-
do, because the moon is meant to be orbiting the Earth. At a certain,
Oh yeah, I suppose.
It's got
Yeah,
its
because
own
the
path.
moon is closer than any other sun.
Yeah,
yeah,
bases.
yeah, of course. So because the moon's well, the bullshit is that the moon's closer.
Yeah, I know,
so
come on.
if you get the moon in, the moon should move faster than any other object in the night sky,
Yeah, no, yeah.
apart from like comets and things
Yeah,
like
anyway,
this,
come.
whatever they are.
Yep.
But yeah, thanks ever so much, Alexander, for that. What's next on the list then, Peter?
Well, let's have a look at the CO2. Let's have a look at some CO2.
Let's have a look at some CO2 demonstrations. Oh, should we do our Zoom in with Peter and Pete?
Oh, we can do, yeah.
Yeah, I mean, if anyone thinks our views and opinions are absolutely wrong, then feel free to join us with a Zoom meeting and we'll have a chat and you can show some proof. We're giving you the opportunity to prove us wrong. Okay, so join us on the Zoom, or
Yeah,
if you
come
want,
on down.
if you want, we'll give you our Discord server address, and you can actually post your proof on our Discord server. And there's lots of people who would probably want to critique your proof. As of yet, no one's come up with any
No.
anything. It's because nobody can prove it. Nobody can do it.
Yeah. But you're more than welcome.
But you're more than welcome to try. I mean, feel free. But not one person.
Are we meant to be getting somebody on?
Yeah,
Zoom?
I've forgotten his name. I've forgotten his name now. Yeah, somebody did mention that they'd like to do a Zoom with us, but he's not gotten back to us. So I hope he does. But he just wants to have a chat about why we think the way we do, why we think the things we do.
Yeah. Because it's easier to have a chat with us on Zoom than to watch a lot of our video.
Absolutely, of course. But he hasn't gotten back to us. But
Anyway.
if he does, we'll record it and we'll upload it.
Anyway, we watched a video some time ago about CO2 and the infrared.
Infrared, absolutely.
By
Yeah, we watched.
Ian Stewart, was it?
Was it Ian Stewart? Yeah, Ian Stewart. Yeah, we watched this video. Ian Stewart demonstrates infrared radiation absorption by CO2. And basically what he has is that he has this tube. Wait there, let's get it all in shot. Wait there. He has... Oh, he's in
An
the way.
infrared
Look,
camera.
he's in the way.
He has an infrared camera. He
Oh,
has
there.
a tube.
Yeah, he's got an infrared camera on the left. He's got a glass tube. And at the ends of the glass tube is cellophane, sealed
Yeah.
with cellophane.
Yeah.
And he's got a candle. And he holds the candle, basically, the lit candle, and he fills up the tube with CO2 gas.
Yeah.
And with the
He's not going to breathe it in.
and with the infrared camera, let's have a little butchers.
So
There's the flame through the infrared camera, and with the CO2 being filled up the tube,
no, the CO2 filling up the tank. The glass
CO2 filling up the tube,
glass tube.
glass tube, it absorbs all of the heat from the candle, which means you can't see the flame.
Yeah.
So
Wow.
that, as far as I'm aware, that is the only demonstration that supports the idea of CO2 being a greenhouse gas.
well,
That
an
is the
absorbing-
only absorbing infrared radiation at 15 micrometers. And allegedly, the only things that will emit infrared radiation at 15 micrometers is the sun, allegedly, and fire.
And also a far
Infrared.
infrared laser.
And a far infrared laser, okay? They're the only things, okay? So the story goes. So what we did, so we're waiting to see another demonstration, aren't we? Because I'd like to see some proof.
Yeah, no, yeah.
I'd like to
There's
see
gotta be
some proof.
something else.
There's got to be something
So
else.
this is the thing. If they're making claims, if science is making claims about that CO2 absorbs infrared radiation, then there should be lots of demonstrations out on YouTube to demonstrate this.
That CO2 does actually absorb infrared radiation,
Yeah.
but you'll find it's sparse. There's not much information out there.
Yeah.
So it tends to, it lends itself to be more implausible that lends itself to be plausible that it's untrue.
Well, yeah. But anyway, on this video, we're filling up a clear polythene bag
With
some
some CO2
CO2.
gas.
And what we're going to do is we're going to shine, or we're going to put the infrared light from the remote control through the bag.
Through the bag, yeah.
To see whether the camera can pick it up.
Absolutely, of course, yeah. And yeah, you can see the infrared
flickering there.
You can see it flickering
so
there.
Switch the light off. Yeah, I can see.
Yeah,
it.
you can see it there.
Yeah.
So we've got CO2 in the bag. You can clearly tell there.
There you go.
And yeah, there you go. And you can still see the light there.
Yeah.
So with the remote control infrared, the CO2 does not absorb that light
wavelength.
That wavelength, that light, you know, doesn't do it. But the camera picks it up anyway. Yeah. The camera detects it, even though it's got an IR cut filter in it.
Oh right, yeah.
Oh right, yeah, which is a bit odd.
Doesn't make sense, does it?
No, it doesn't make sense. It's got an infrared. The camera's got an infrared cut filter, but
it's supposed to cut out infrared light, so you shouldn't be able to see the light from the remote control.
Yeah, sure. But anyway, that was our number one. What we did. Why are we holding that? Why are you holding that like that?
Doesn't matter. Because you just want to test that it is CO2 in there.
Yeah, we just want to show that we've got CO2 in there, just to demonstrate that there's... Yeah, there you go. So it went out. Okay, so that was demo number one. And demo number two is this one, which we did this morning. And what we've got this candle in the background there. And we've got a foot pump. Yeah, we've got a foot pump there. Yeah, oh no, it's not a foot pump. It's like a hand pump. It's like a
bicycle pump.
Yeah, but it's like one of those pumps. Yeah, it's not a foot pump. It's one of those kind of pumps. And what we've attached a tube to it, and we're going to fill up just air in this polythene bag. Okay, let's fill it up. There we go. So the bag's getting.
Because we want to see the difference
between
a polythene bag filled with air and a polythene bag filled with CO2
to see if there is
when we're looking at a flame.
Absolutely, of course.
Through our thermal imaging camera.
So there's the. So we're setting up just the same as Ian Stewart, aren't we? Really,
basically, yeah.
We've got thermal imaging cameras. It's exactly what he has. There's a flame, so we've got the candle flame there, and here's the bag with the air inside it from the pump. And, well, you know, I mean, there's not much difference, really, is there? You know, minor.
Well, look, it does look as though it reduces the glare of it.
Yeah, minor difference, isn't it?
Yeah.
Yeah, it makes a difference, yeah. There is a difference, but minor. Okay?
And that's in air.
And that's with air. Okay, but it would make sense anyway, because there's something between the candle and the thermal imaging camera.
Yeah.
You're placing something. It doesn't matter what it is, but you're placing something. So it's going to affect it to some degree. Okay, so that's that
next one.
So the next one, what we do is we fill the bag up with CO2. Now, if anyone says that the bag had air in it, the CO2 would actually, purge the bag of air anyway. So you can't really use that as an excuse. So I'm quite satisfied the bag was filled with CO2. Okay.
Come on, move it forward. Come on.
Let's move it forward.
Move it forward. People don't want to be waiting.
There we go. Look at that. It's like a balloon. Up and away in my beautiful CO2 balloon. Wouldn't get very high though, would it?
Yep.
Okay, there we go. And there we go. We've got the bag. Tying it all up. There we go. Filled with CO2. Okay, now let's see if it makes a difference. Let's see if there is a difference. So we've got the infrared camera in the way. Wait there. Let's just drop the camera down. There we go. And there. Now here goes the bag.
Here we go.
And well, not really. I can't really say that there's.
Well, it's a bit similar to the one before, isn't it?
Yeah, it's a bit similar. Yeah, sure.
But it doesn't block it out, does it?
Doesn't
absorb the heat. If it absorbed the heat, the CO2 absorbed the heat from the flame, you wouldn't see the flame.
Sure. Yeah, of course. Yeah. Oh, because the thermometer, the actual crosshair for the thermometer calibration or measurement is actually measuring the bag the temperature of the bag and not the candle.
Oh, right, yeah.
That's why it goes down. That's why the temperature drops down when the bag is placed in front of it. But there's not much difference. So we can't really say that, that CO2 does actually absorb infrared radiation.
Yeah.
So, but one of the things we've also got to ask ourselves, well, how is it possible we can demonstrate that a candle flame emits infrared radiation?
Oh, right, yeah.
Yeah. How could anybody prove that a candle flame emits infrared radiation? Now, if anyone's got any ideas on how we can do that, then please feel free to drop a comment below. They say science will tell you, okay, that a candle flame or fire emits 15 micrometers of infrared radiation.
Yeah. Far
infrared radiation. So how can that be proved?
And it's actually visible
Any ideas?
light. It's actually visible light because you can actually see the flame.
Well, you can see the flame, but if anyone's got any ideas how it can be proved, let us know. Leave a comment below.
Oh, because you've got to remember, if there's no flame, there's no heat.
Absolutely, yeah. No flame, no heat. Absolutely, of course. Of course. But, we still can't find... and the worst thing is that we've done some research and there's nothing else that emits 15 micrometers of infrared, apparently.
Yeah, a far infrared laser.
Only a far infrared laser. Yeah, that's anything that man makes.
Yeah.
And that actually does that. Yeah, of course. But there's
Nothing
no
else.
gadget or device that I could buy that will do that. So I can't.
Oh, what about PIR sensor?
Oh, a PIR sensor will detect 15 micrometers of infrared. But what we need to do is we need to
emit it.
So if you had a candle? If you had a candle and you had the PIR sensor on the candle flame and you blew out the candle flame, it should trigger a response.
Yeah, but it's a motion detector, so it would pick up the motion.
Yeah, but it works on 15 micrometers.
No, well, when we looked at PIRs, we are looking at it looks at lights.
Sure.
It looks at the light because it magnifies the light that goes into the sensor.
Oh, because they use Fresnel lenses, don't they?
Yeah, and it can detect any change in light and shade.
Light and shade, absolutely, of course.
Basically.
So if the candle goes out, the candle flame,
It'll be dark, won't it?
Right, it'll be dark. So they should be able to detect it.
But if anyone knows how we can create 15 micrometers,
absolutely, or what
radiation,
IR,
yeah, let us know without using a laser.
Absolutely, of course. So what's next then, Peter?
Blue marble.
Oh, blue marble science. Now, yeah, of course. Now you'll like this one. Oh, excuse me. Had a lovely dinner. That's all.
Blue marble.
Now, who goes? Oh, unicorn laser eyes. I'll just ask us to have a little look at this video here. Blue Marble Live. Did we record an earthquake? Blue Marble Science. Now, Blue Marble Science has got nothing else better to do in his life than build
a torsion balance.
Because
he's got a workshop.
He's got a workshop.
He's into his woodworking.
Absolutely. He's got fuck all really that's meaningful to do in his life. So he ends up building a Cavendish torsion balance because he's pissed off with a lot of flat earthers saying the Earth's flat and Cavendish is a load of bullshit and all this kind of rubbish.
But what he fails to realise is that if he read Cavendish's paper, he would actually read that Cavendish did recognise that temperature plays a role in the motion of the the spheres.
Well, you see, absolutely.
And the trouble is with Blue Marble, and that is he's made his torsion balance out of all different materials.
Yeah, sure. But the thing is that if you place a cold object next to a warm object, you're obviously going to have some kind of interaction between the two, where, for example, the heat will want to move towards the cold. For example, well, that will create some kind of let's use the term very loosely, an energy draft, where it will move from one to the other. So you can argue
a differential,
and a temperature differential. Because of the temperature differential, you might find, or I'm sure you do well indeed find, there will be the warmer object, for example, could be attracted to the colder object.
Yeah.
Which means you're going to get movement. See, what he should do is that he should use different objects.
Yeah, but the trouble is,
he should use objects of a different mass as his counterweights, as it were.
yeah. But the trouble is, you can't measure. You can only measure the surface of the spheres or the objects that he's using as weights. He can only measure the surface. He can't measure the internal.
He can't measure actually the absolutely, yeah. He can't measure the true temperature of an object. Say, I don't know, 2 kilograms.
Yeah.
He
A
can't-
bowling ball.
A bowling ball.
You could use a bowling ball
or a cannonball.
and a cannonball,
Yeah.
for example. But he can't measure the internals,
The internal. Yeah, but the
temperature of each object.
the bowling ball's hollow.
But he still can't measure the internal temperature of it unless he drilled a hole and put a thermometer inside.
But he's only getting a sample. He's only getting a bit where he puts the metal in.
He'll only.
The electrode.
All I'm saying is that he'll only be able to get a measurement of the temperature of the surface.
Yeah, he'll only get.
That's all I'm saying.
But
Which could be different to what it is inside.
absolutely, it's something inherent in objects, you know. But anyway, now anyway, so during the live recording, he actually picks up an aberration in the laser light. So let's just mute this, and then you can see that the laser light starts to do this at some point, which as it moves across. Okay, it goes like that. So he's wondering what it is, you know. Well, what is it? And you know,
And it happens more than once.
it just continues, doesn't it? It just continues throughout the lot. I mean, I'm not going into it.
Well, it's
I
not
don't know what's
continual.
It's not continual, but it
Continuous.
goes. I think it starts. Wait there. Let's just go from here.
Oh,
Yeah, you can see it moving
there.
up and down there. It's moving up
840.
at 840. It's moving up and down there. And let's wait there. Hopefully we can. Oh, yeah, there you go. It's moving up and down there at 848. It's moving up and down there. Now he puts this aberration down to
Him picking up the earthquake in Haiti,
absolutely. A
2,200 kilometres away.
Yeah, a magnitude 7.2 earthquake struck Haiti in 8:29 at 8:38. Timestamp 38 minutes in the video. We saw an unexplained disturbance in the torsion balance. It appears plausible that we may have inadvertently recorded a seismic event some 2,200 kilometres away. I'm not 100% sure on this, but so far I've no other explanation for what we witnessed. Okay.
Bum, bum, bum.
So I asked, what made you think it was an earthquake? Movement of the laser at 44, you know, or 38.
Or
you know,
38, yeah.
that's all I'm saying. And then he asked, is that a statement or a question or your usual incoherent babbling? And I'm thinking, you know, it's talking to these people.
I'm only asking what made you think it's the earthquake.
Absolutely, you're talking to people who've got mental health problems because they can't even understand a question when they read it. You know,
Yeah, but I mean, I can understand why he thinks it was the earthquake.
I can understand
I
that.
can understand.
But why couldn't he have just said, you know, what makes you think it was an earthquake? Because an earthquake, he should have said that an earthquake was recorded in Haiti at the same time when I did the thingy. That's what he should have said. So no, but anyway,
The main point about this torsion balance is if you go up and have a look at seismometers.
seismometers. Sorry, I didn't get the page up, did I?
He's saying he's picked up the indication that there was an earthquake,
Earthquake.
and believe it or not, seismometers are actually made similar to a torsion balance.
Yeah, sure.
Basically.
Yeah, modern instruments. Where
Hey, you want to go up?
yeah,
Yes.
oh, there you go. We're on there. Yeah. I think we need to go on there.
An early special purpose seismometer consisted of a large stationary pendulum.
Sorry, let's make it
Stationary pendulum. We've heard of one of those before. Pendulum.
Pendulum.
Full court pendulum.
Full court, yeah, sure. With a stylus on the
The
bottom.
stylus on the bottom. So a little, say, a pencil on the bottom.
As the Earth started to move, the heavy mass of the pendulum had the inertia to stay still.
within the frame.
Yeah.
So the frame was moving, but the pendulum wasn't.
Yeah.
So there obviously was a piece of paper underneath or something to record on. So as the frame was moving, it was recording the movement.
There was,
of the Earth.
a piece of smoked glass with carbon soot on it, so you could etch onto the surface any kind of movement.
While not sensitive enough to detect distant earthquakes, so it does actually make you wonder how we managed to detect an earthquake 2,200 kilometres away.
Sure.
This instrument could indicate the direction of the pressure waves and thus help find the epicentre of a local quake. So that's just an example of what they used to detect earthquakes.
So
Now think about this. A full court pendulum works on a similar principle. The pendulum is swinging,
or the torsion balance.
let's say the pendulum is swinging, but it's only swinging simply because...
Hold on. Wait a minute. You mean full court pendulum.
Yeah.
I thought you meant
Cavendish.
Cavendish.
Swinging, but as it's swinging, it's precessing, and it's precessing due to the motion of the Earth.
Allegedly.
Now, if this seismometer had a pendulum, stationary pendulum, with a stylus on the bottom that was fitted within a frame, the frame would be rotating.
Yeah, the frame should be rotating.
Would it not? Because of the Earth rotating?
Absolutely,
Yeah.
of course, yeah. Because the pendulum's free to move in any direction, just like a full court pendulum. But so these seismometers really, don't really take into account the Coriolis effect, the alleged Coriolis effect.
So it stands to reason that Blue Marble Science's torsion balance should be affected by
The Coriolis effect.
Yeah, the Earth's rotation.
So we'd like to know what has Blue Marble Science actually done by means of factoring out the effects of the Coriolis effect to affect his torsion balance.
You can't. It's impossible.
Absolutely, of
And
course.
this is an example where one bit of science
Or maybe, I know what he should do.
contradicts
Another
bit.
Yeah,
of
maybe
science.
what he should do is that he should take his torsion spring apparatus and take it to the other hemisphere to see if it moves in the opposite direction.
Oh right, yeah, but it won't.
I know it won't, but maybe he should.
Oh right, yeah, maybe you should.
Maybe he should. Maybe he should go and see Wolfie 6020
Oh right, yeah.
and go and stay around his place, ship it off, crate it off into a crate and ship it off, or put it on a plane. And then send it to Wolfie and let Wolfie have a go on it, or let Wolfie build one.
Yeah, I know. But it's clear from looking at the information of what they used to make seismometers, and that is that pendulum didn't move.
Yeah, the pendulum didn't move, but
it was only the frame, and the frame actually moved slightly if it could hear if the ground moved.
Yeah, the pendulum would only move if there was enough vibration in the frame.
If the Earth is rotating, if the full court pendulum is able to detect the Earth's rotation, then that frame would move around that pendulum within the size seismometer.
Anyway, getting back to the point, I mean, it does seem plausible that old Blue Marble Science did pick up or detect some kind of tremor.
What he should
earthquake.
do. What he should do really is that he should find his location. Get his location, and then from there to Haiti, and then see whether there was a seismometer in between those two
I'll see whether there was a recording station.
Recording station between them, so that they would actually record.
Yeah, sure, and get some data.
And then that would be more likely that he was recording.
Absolutely. But I'd tell you, it's quite possible that you could actually use these as a way of. Well, you've got to, haven't you?
Well,
if you have an earthquake just outside your front door, kind of thing, that laser level's going to just go like this, isn't it?
Yeah.
The laser, the laser light.
Yeah, I know. Yeah, but he could have been jumping up and down.
Well, he could have been, absolutely, of course. He could have been just been walking up and down in his garage. You know what I mean? Pacing about while he's waiting for his Cavendish experiment.
He could be quite a big bloke, because he kind of talks like this. You see.
Oh yeah, of course. Yeah. Well, I didn't know what to do, but
kind of big.
yeah, I think we've got an earthquake on the Richter scale, 9.4.
So thanks, Union Laser Eyes.
Sure,
for that
but that's there. It's possible. But the thing is that how is he going to prove it? This is the main thing.
Yeah.
Like with a lot of things, it's all right coming up with ideas, but you've got to prove them at the end of the day.
Let's go.
But it's a plausible idea anyway. And the last one, I suppose.
Let's click that off.
I don't want to click any off until we've done it. So yes, of course, this guy can't prove light is electromagnetic. Of course, yes. Believe it or not, this guy, Dr. Donald Lincoln, from Fermilab, named after Enrico Fermi of the nuclear,
who built the first nuclear reactor.
Absolutely, of course, fame. This guy, he's got a doctorate in whatever,
nuclear physics
or physics.
Probably.
Or physics, absolutely can't prove light is electromagnetic.
Yeah.
Okay. Totally ridiculous.
Anyway, come on,
for us, really. Well, understandable for us, really. But
now, do we need to go and talk about the Faraday effect?
Should we talk about the Faraday effect?
Yeah, because that's important now.
Here you go. Let's go from here.
The Faraday effect.
The Faraday defect.
Faraday.
Yeah, the Faraday. Which one did we look at?
That's the one.
There we go. We watched this one. Everyone's seen this one before.
The Faraday effect. Very quick.
Faraday effect. There we go. So what happens is they've got.
Hold on. Faraday effect is a magneto-optic effect which shows the interaction between light and magnetic field in a medium. It causes a rotation of the plane of polarization of light.
Absolutely, of course. So
basically, the light rotates.
Light rotates. Okay.
In other words, the light is affected by the magnetic field.
Yeah, that's all you've got to know. According to the Faraday effect, according to physics, according to the academia, according to the education, light is affected by an electromagnetic field.
Yeah, basically.
Yeah, basically. That's what it puts down. Yeah. Right, okay. So now that we've done that, okay, we'll go back to Mr. Don
Lincoln.
Dr. Donald. And we were given this video by William Connor to have a look at, and we've looked at it, and why does light bend when it enters glass? Now, I mean, it's an interesting kind of video, isn't it? Do you not think it's an interesting video?
Because you kind of look at it and you kind of think, well, it's an interesting question.
It's an interesting. Why does light bend when it enters glass? I mean, they've made so many videos, and lots of people ask them on their videos, well, why does light bend when it enters glass?
But most people would come up with the idea that because glass is a thicker medium.
Glass is a different medium
than air. So it's bound to.
So it's bound to bend.
It's bound to, no, not bend, but it's bound to
refract,
pass through in a different way,
pass through at a different angle.
Yeah,
of course. But anyway, so what does he talk about through this rubbish?
But this guy wants to answer why.
Why does it? So there's the angle of diffraction.
Angle, and the transmitted.
There's the angle of refraction, we should say.
Yeah.
Angle of refraction he's demonstrating there. Talks about Snell's law. And he talks about basically Snellius. Not Smellius, but Snellius. And he gives the analogy that basically of a lifeguard wanting to save someone.
He gives three explanations why. Most common explanations why the light bends as it's travelling through glass, and one of them is the. It
will follow its path of least resistance.
Is the You want to move it back so people can see
No, I
what
don't
those
think.
three things are.
No, he hasn't mentioned.
He
Oh,
does,
yes,
yeah.
I'll call it Fermat's principle.
Now, Fermat's principle is just saying that light will travel the quickest, the easiest path from A to B.
Yeah, the least resistance, path of least
So
resistance.
he's given an example. They always give you like a theoretical example. Here we
Yeah.
go. A lifeguard on a beach, to save the person drowning in the water, they will run along the beach the quickest, so that they haven't got to swim as far to reach the person, because they know that they're going to, when they're in the water swimming, it's going to slow them down.
Yeah, so basically they can run faster on the beach. They can move quicker on the beach, so they'll make up most of the distance on the beach, and then make up the shorter distance in the water, because they can they swim at a slower rate.
Yeah.
So that's one idea as to why the light bends.
Yeah. The other one is
the other one, we've got marching soldier analogy, and this is where you've got this is where you get the soldiers marching in a row, you know, in their ranks, you know.
And they're going easy terrain now. They're going to go onto the mud.
They're going into mud, which will slow them down. So they're obviously going to, you know, be slower, and the people behind them will catch them up. So they'll change angle,
change direction.
They'll change direction. I mean, it's a good little idea, another idea, but they don't accept that to be true at all.
And the other one is Huygens principle.
And the other one, the last one,
Huygens.
Is Huygens. He was Dutch, I'm sure. Christian Huygens, who came up with the wave theory, who introduced the wave theory of light to begin with. Now, all of a sudden, you get this animation here with the air and the glass, and it looks as if the glass has got a hole in it.
Oh right, yeah.
For the light to propagate through. Now you've got more. You've got three holes now, where the light waves can propagate through. So I don't know how the glass has got holes in it.
Neither do I. Well,
you know,
that's because they're trying to demonstrate it in a diagram.
Yeah, but you know, you can't do that really. Yeah. So it doesn't really wash Huygens' principle, Huygens' idea, because you can have interference patterns going all over the place, can't you? Yeah. As we see here, you know, you can have them going all over the place, won't they? Like here, for example. Yeah. You can get interference patterns going off in lots of directions.
Because they're trying to, because they know the angle of refraction, because they've studied them.
Yeah, they've studied the angles of refraction.
From
of course,
air through glass. They've studied the angle of refraction.
Yeah, and it's always consistent.
It's always consistent. So
if you use the same medium.
Yeah. So they've got the basis there. So all they have to do is think up explanations to account for
why
the consistent
observation. The consistent observations. So basically, after dismissing all of the other ones, should we actually have a listen to this? I think we should actually have a listen to this. And after what they reach, what's his name? Maxwell's equations, don't they?
Yeah. Come on.
So let's just play it from here. So are you listening? Well, this is not copywritten, so we're okay here. So we can play this. Just want to ensure that that's it. Okay.
Seen as explanations of the cause of refraction given by people who really do know some physics. So what's the real answer? It turns out that the only way to really answer the question of why light bends when it goes from air to glass is to get serious about the nature of light and to embrace the fact that it is made of oscillating electromagnetic fields, and that means you need Maxwell's equations. Because this isn't a full-blown physics class, I'm going to focus only on the electric fields. And I'm not going to do the derivation because that's the fun part. I'll leave that to you. But the big ideas are actually pretty...
You should let people watch this because this is important.
Yeah, they're watching it, aren't
they? Yeah, but it's important.
Yeah, listen now.
You shouldn't muck about.
Straightforward. You start with Maxwell's equations, which are always beautiful to see. They're a little scary looking, but the question we're trying to answer is an easy one, which makes the whole thing a lot simpler than you'd imagine. In fact, we're going to need only the bottom two equations. So let's see what's going on. We start with light going from air to glass, hitting the surface at an angle. In our figure, we can replace the waves with the direction of motion. Now it turns out that the electric field of light is perpendicular to the direction that light is traveling, and we can add that field direction to the diagram. And it's very important to remember that this field has a component both parallel to the surface of the glass and one that is perpendicular to the glass. And here is where Maxwell's equations come into play. Two copies of the equations are written here, one that covers when light is traveling in air and one where it is traveling in glass. So here's the key point. The surface belongs to both the air region and the glass region. This means that at the surface, the equations on the top and the equations on the bottom have to apply. And with that little bit of calculus, you can find two important restrictions. The first is that the electric field parallel to the surface of the glass has to be the same in the air and the glass. And similarly, perpendicular to the surface, what has to be the same is the electric field times this epsilon, which is different for each material and depends on its molecular makeup. We can then manipulate these equations to see what the electric field in glass should look like. Because epsilon is bigger in glass than in air, that means that the perpendicular electric field in glass has to be smaller than it is in air. Now we remember that the direction the light travels is perpendicular to the electric field, so we can put in an arrow to show the direction light must travel in the glass. And finally, we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air.
Well, the epsilon in glass is bigger than it is in air.
Is that right? Or was it bigger in air than in...
Well, I'll just go back.
Let's go back. Let's just play that again. Here we go.
A transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air.
Yeah, because if you go back in that bottom left-hand corner, E differs for each material. Epsilon in air is 1, whereas epsilon in glass is
more than one. Absolutely, of course. So the reason why, if you was James Clerk Maxwell, the reason why light bends as it's going through a different medium like glass is because of epsilon.
But what's epsilon?
Okay, let's have a little look. Epsilon.
But epsilon. Here we go.
Wait there. Yeah, epsilon.
That's what we need to put.
I was going to put
Epsilon.
Epsilon.
Really?
Well,
What does epsilon mean?
no, you want the Merriam-Webster. There you go.
Definition of epsilon.
Definition. Oh, here we go. Wait there. Let's just click off.
The fifth letter of the Greek alphabet.
An arbitrarily small positive quantity in mathematical analysis. Well, what does that mean?
What's
An arbitrarily small positive quantity in mathematical analysis. Arbitrary means it's just
arbitrary?
arbitrary. It
Doesn't matter whether it's
doesn't
there or
matter.
not.
Meaningless. A small positive quantity. Well, what quantity is that?
Sounds like they've just made it up.
No, it sounds as if they don't know what it is. All they're saying, as far this is the thing is.
Yeah, but you could use the density of glass is more than the density in air.
Yeah, that's what the epsilon refers to. Density. Really, that's what it means. What it's basically saying, really, is that glass is denser than air, and that's why the light bends.
Yeah, but the interesting part about this, and that is the idea that there's an electric. If you go back to before they put it there.
Yeah, there. Okay. We'll switch the volume off now.
If you go back here, it says here electric field of light.
Now, where does he get that information from? An electric field of light.
Now, we have to remember that James Clerk Maxwell was best buddies with Michael Faraday.
Absolutely.
Who did the Faraday effect in that demonstration that we just showed everybody.
Or who thought up that demonstration.
Did we show people the
we did show
Faraday effect?
Yeah, no, we showed the video, but we only showed...
Let's go back to the video.
The Faraday effect. Yeah, we just showed this video here.
It's a magneto-optic effect which shows the interaction between light and a magnetic field in a medium. It causes a rotation of the plane of polarization of light.
Absolutely, of course, yeah.
Basically.
So, but yeah, I mean, people have seen this before, you know.
But let's just quickly go over it. They've got two induction coils, creating electric fields,
and a magnetic field.
They have they've got a whole there's more or less a tube going all the way, clear tube going all the way through.
Well, you can see all the way through. Two coils right to the flame.
And they place
from his eyepiece.
They place a dense piece of glass between the two coils.
Yeah, and the glass he placed right there.
Right in the centre.
There's a block of glass, dense glass between the two.
Right in the centre.
There we go. Wait there. Let's put it. He's put it there. Okay, you can just see that.
And in between that, he's got a couple of polarisers.
And at the end of where his eyepiece is, there's a couple of polarisers to basically cut out the light. And every time the
current is switched
on, he can see the light from the candle.
Yeah, the magnetic field rotates.
Absolutely, of course. Yeah,
the magnetic field rotates the plane of polarisation of light, and therefore
there is no extinction.
He's able to see the flame.
Absolutely, of course. Yeah,
through the polarisers.
Yeah, sure. Absolutely, of course. Yeah, but we think that's all rubbish.
So in their understanding is this experiment that Faraday carried out that to him convinced him that light is electromagnetic,
and convinced others,
especially James Clerk Maxwell probably used the idea of the electric fields, electromagnetic
or light
fields,
being an electromagnetic phenomenon.
Yeah, to work out its speed and work out lots of things about it.
Absolutely, of course, yeah. You create mathematical equations.
Yeah,
absolutely. But the thing is that when we get down to this, but where's the proof that light has an electric field of light? An electric field.
Sure.
They were talking magnetic field, but now it's an electric field.
Oh, a magneto-optic effect.
It's a magneto-optic effect, and now it's an electric field of light. You know, there's something, you know, here, the light is allegedly affected by a magnetic field. Not by electricity, but by a magnetic field. And, you know, in this video, but in here, they talk about an electric field of light.
But let's just move forward till he goes on to the other diagram.
Oh, now a lot of people are probably thinking to themselves after watching the bit about the analysis of epsilon
and applying Maxwell's equations.
A lot of people are probably thinking to themselves, well, how does that?
How does that prove that light is electromagnetic?
Absolutely. So, I think let's go back to where we were. Yeah, that's about here, wasn't it?
Yeah, just play it from
here. Well, let's just play it from here. Okay, so I want to ensure we've got everything in. Okay, listen carefully.
And put in an arrow to show the direction light must travel in the glass. And finally, we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air. Okay, what I just showed you is an equation thing. You're probably asking yourself what that epsilon actually physically means. It's there because of how the electric fields from the light interacts with the matter in the glass.
Right, well, straight away you've got to ask yourself, well, what electric field is he talking about?
Not only that, he's actually admitting, whether it's true or not is a different matter, but he's actually admitting that the electric field affects the material.
No, there's an electric field within the material.
Yeah.
Absolutely, of course. So
when we go back to the
Faraday
effect,
we
can apply this understanding to the Faraday effect, and we can safely assume or put forward that the magnetic field or the electric field is affecting that piece of glass.
That piece of glass, absolutely, of course. The piece of dense glass that is placed between the two coils, this one here.
Yeah.
You know, this piece of glass here, the dense glass.
And
absolutely, of course.
In our understanding, the reason why you can see you get the rotation of plane of polarization of light within this when the current is switched on is because, well, we think is because the material magnifies.
I wonder if it accelerates.
We could intensify the light,
Or it could or accelerate the light through the medium, through the glass.
It could well do, yeah.
Could do. I mean, who knows?
Who knows?
But when we do look at this information, they're actually suggesting or indicating that you can have an electric field in a material. Okay.
Especially when it's placed within two induction coils.
Well, when there's a magnetic field present.
Yeah, basically.
Absolutely, of course. But the most striking part about this is that they're not showing you the diagrams or the animations, not showing the light bending. The light's actually coming in
this
straight
in this demonstration
and hitting the glass medium straight on.
Yeah, in this diagram.
They don't do it from an angle,
No.
do they? Which is what one would have thought they would do.
Yeah, because they can't explain it.
Because they can't explain it.
They can't prove it.
They can't prove it. This is the main thing. So let's just go back and let's watch the whole lot again, okay?
Probably asking yourself what that epsilon actually physically means. It's there because of how the electric fields from the light interacts with the matter in the glass. You start out with glass with no electric field in it. The glass has charges in it, but they're arranged in a random way. But when you send light in, you impose an electric field on it. That field makes the charges move around, which sets up a counterbalancing electric field from the charges. The result is that the electric field in the glass is lower than it is in air because of how the electric field from the glass is in the opposite direction. And this is the reason that the perpendicular electric field is lower in glass. And that, my friends, is why light bends when it goes from air to glass. It's not because of many of the ordinary explanations.
Yeah, I mean, basically what he's saying is that the glass is denser than the air. That's essentially what he's saying,
Right.
But he's saying it in such a way that
In a technical way.
In a technical way.
Yeah.
But
But the thing is that he's not actually proving.
he's not proving any of what this is. He's not proving any of this to be true. He doesn't prove it with a demonstration.
Yeah, no, yeah.
He doesn't prove anything that what he said in this video at all.
With a demonstration.
With a demonstration.
No.
All of these Maxwell equations. How has he proved Maxwell equations to be true? This electric field of light. I mean, let's have a candle, okay, and let's see a beam of light coming from a candle actually being diffracted in glass, and you can see that electric field. You can detect it.
Yeah.
What are you going to use to detect it with?
Yeah. So
what would you use to detect it with?
Yeah,
Let us know. Leave a comment below.
We'd like to ask everybody, how would you demonstrate that light is electromagnetic?
Absolutely. How would you
demonstrate it to somebody else?
This is for everyone out there.
We're not talking about using calculus or formula or anything like that.
Okay.
Or diagrams like this.
Yeah. The claim is.
How would you demonstrate to somebody to prove that light is electromagnetic?
Absolutely, of course. Yeah. How would you do it? Okay. Get a candle. What are you going to do with it? What are you going to do with a candle?
What are you going to do with it?
Think about it logically. You've got to. If you can't prove it, then obviously there's something wrong with the science.
If you can't prove it, lose it.
Lose it. If you can't prove it, lose it. Absolutely, of course. That's a good little saying, that is. If you can't prove it, lose it. Absolutely, of course. But let us know below. Leave a comment below. Let us know what you think. If you think you can prove light is electromagnetic, or even has an electric field around it, we'd love to see your evidence. We'd love to see your proof.
Oh, because we have been looking at other videos about electric fields.
Sure.
And they have demonstrations with the oil.
With the oil, yeah, sure. But that's not light, though, is it?
No.
That's not light. We're only specifically talking about light,
Light,
because the claim is light is electromagnetic. So we'd like to see proof that light is electromagnetic, and hasn't just been explained away by electromagnetism, the understanding of electromagnetism, like Faraday did, and Maxwell, and Mr. Don Lincoln.
Yeah.
Absolutely, of course. So there we have it.
There we
isn't
go,
it?
yeah.
So we've done quite well this evening. So thanks ever so much. And there you have it for another week. So always remember till next time, if something doesn't make sense, like people thinking that light is electromagnetic or light emits an electric field.
Or thinking that water, a sample of water, contains dissolved oxygen in it.
Absolutely.
And you have to put a couple of chemical tablets into the water. And all you're doing is just measuring the pH of it.
Yeah, or if you thought that oxygen is a constituent of the air. That reminds me as well, I was talking to somebody the other day, and we were talking about how much kind of like rubbish there is in society, lots of bullshit claims, and we were talking about one particular claim and blah, 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 and through the conversation I said to him, but why, hey, you're talking to someone who thinks there's no oxygen as a constituent of the air, and it just went over him. He didn't even register that I said that.
Yeah, I know. Yeah.
Amazing. It's amazing how people just don't listen when they're talking to you.
It's because he's in his own little world.
Yeah, he's in his own little dream world. Because it's his bubble, it's his comfort zone.
Yeah.
It protects him from the harsh reality of life.
Absolutely. Yeah.
Or the harsh reality of his life.
Oh, right, yeah.
Absolutely, of course. But, it's all rubbish, isn't it?
Yeah,
of course.
There's oxygen in the air.
Oxygen in the
Water's
air.
made of hydrogen and oxygen.
Absolutely, of course. But there you have it. So,
I think the moon orbits the Earth.
Oh, the moon orbiting the Earth. Yeah, that's a good one. Lots of mentally ill people. There's an awful lot of mentally ill people walking the Earth.
Well, I think we best leave them alone.
Absolutely, of course. So thanks
week.
ever so much. Yeah, it's all nonsense, isn't it? Of course. So we'll see you next time.
Okay.
Bye.
Ta-ra.
The Earth isn't round, it's flat.
How do you know?
I've observed it in all my travels over Europe. It's flat. Everywhere it's flat.